Hi, my name is Jordan and I would like to talk about the recent experiment that I conducted regarding the making of ferrofluid. And ferrofluid is a fluid which has the properties of both liquid as well as the magnetic properties of the solid. These ferrofluids contain the tiny particles of magnetic particles which are suspended in the liquid. These ferrofluids were originally discovered by NASA in 1960, and these ferrofluids contain magnetite, which can be prepared by combining the Fe2 and Fe3 salt in various proportions in a basic solution, which precipitates Fe3O4 from the solution. And in order to remain suspended in the solution, the size of the magnetite particles must be small. Also, magnetic and van der Waals force, as well as magnetic force of interaction, must be overcome so to prevent the particle from agglomerating. For this is the thermal motion of the particle. It must be smaller than 10 nanometer in diameter. When the distance between particles is closest, the van der Waals force of interaction is the greatest. To prevent the particle from agglomerating due to magnetic force and van der Waals force, the particles should be well separated from one another. For this would add a liquid surfactant to the medium, which increases the electrostatic repulsion between the particles. For example, cis oleic acid can be used as a surfactant to oil based on ferrofluids. For my experiment, I used vegetable oil, but I wanted to give you that example. Ferrofluid is a black solvent-based liquid that, in presence of a magnetic field, becomes strongly magnetized. The fluid is made out of nanomagnetic particles coated in an anti-stick or surfactant compound suspended in a carrier, commonly an organic solvent. And for mechanical purposes, it can be used in hard drives and speakers as a lubricant. Ferrofluid consists of nanoscale particles, which I mentioned before, 10 nanometers in diameter, of a compound of iron in both +2 and +3 oxidation states, dispersed in a liquid, oil, or water that are usually coated with a surfactant, resulting in a colloidal dispersion. It's usually going to be oil, and of course, as I mentioned in this experiment, I used vegetable oil. But also particles are held by a strong magnetic field, and all electron spins are paired in diamagnetism. In paramagnetism, particles are attracted by a strong magnetic field, and unpaired electron spins exist in the particles, and iron is paramagnetic. Ferromagnetism, however, results from opposing but unequal magnetic moments of the atoms in different sublattices, Fe2+ and Fe3+. Ferromagnetism, a macroscopic scale. The substance can be magnetized, and iron is ferromagnetic. How machines detect the value of currency is an example of why this is important in mentioning that specific fact. Ferrofluid is used in the manufacturing of magnetic ink, and a ferrofluid consists of colloidal parts nanoscale composed of iron 2 and iron 3 compounds such as FeCl2 and FeCl3. A ferrofluid is attracted by a magnetic force field, but does not become permanently magnetized. And to show the ferrofluid present in ink, a US dollar, for example, can be added to water and mixed into a blender, and the mixture is then transferred to a clear plastic cup and stirred while holding a strong magnetic field on the outside of the cup, and the fluid ferrofluid could adhere to the inside of the cupboard wall, but that's just one example, one experiment that can be done, but what was actually done was vegetable oil and ink were combined in a solution, specifically ink toner, and I used some rare earth magnet in order to create a chemical reaction with the mixed ink and oil solution, which I previously explained in the information beforehand, and I'd like to talk even more about it. But I want to give you an overview of the experiment, what I actually did. So there are several key interactions that happened in the experiment that I conducted. Magnetite acts as the magnetite does and is attracted/repelled based on the magnetic field, and all of those little nanoparticles respond to the force and start moving, allowing the solution to be able to move when the magnet is in place. I poured the solution of the oil and the ink toner on the table and put a magnet underneath, and then the solution ended up spiking up and moving with the magnet as predicted. It was very interesting, but it was extremely messy. And another key interaction is the surfactant, which is the same kind of chemical used in detergent to move stains, interestingly enough, remains ultra slippery and refuses to let the nanoparticles attract to each other. And they keep slipping away while they move, forming little quick bonds with the surfactant. It's said to become a special type of ligand or coordinate bond with a metal atom, and at the same time the surface of the ferrofluid experiences a lot of tension, which allows the fluid to maintain the shape for longer periods of time when it was drawn out. Meanwhile, van der Waals forces are having a similar effect on the molecules within the mixture, allowing them to maintain a surprising amount of cohesion as the ferrofluid moves. On top of it all, as the ferrofluid is being pulled by the magnetic force, the heaviest parts are also being dragged back down by gravity at the same time. Ink toner, also used in laser printers, contains about 40% of fine iron dust on the nanoscale, which usually has a diameter of about 10 nanometers or less. Just for clarification's sake, even though I probably mentioned that before, and nanoparticles of magnetite and hamite contain iron. The ink toner is mixed with vegetable oil to make a viscous colloidal liquid known as ferrofluid, and therefore ferrofluids are colloidal liquids made up of ferromagnetic particles with fluids that are usually organic, like oil and water. As the name suggests, ferrofluids are composed of ferromagnetic particles, surfactant, and carrier fluid, such as vegetable oil. Ferromagnetic particles are used because of their large magnetic permeability compared to other classifications of magnets. Essentially, the resultant magnetic field is orders of magnitude larger than the induced magnetic field. This becomes important when manipulating ferrofluids under moderate controlled magnetic fields. Typical ferromagnetic materials consist of iron, nickel, and cobalt-based metals, and occasionally rare earth metals such as neodymium and chromium, and iron oxide compounds such as magnetite, which is Fe3O4. And of course, as I mentioned in the experiment, I used a rare earth magnet, so that's how that information pertains to the experiment. Ferromagnetism is caused by long-range atomic scale ordering that causes unpaired electrons to align parallel with each other in a domain, and these domains or regions, about 1 millimeter linear dimension of magnetic alignment, are randomly oriented and confined within the bulk of material, leading to a magnetic field of 0. However, under an external magnetic field, these domains align, causing an amplification of an applied magnetic field, These domains created under an atomic scale long range may span over long numbers of atoms. However, to make a ferromagnetic material fluid for our purposes was explained previously with the oil and the toner and using the rare earth magnet to make the reaction, the magnetic fields happen. And this is about all the information I have that's relevant for the experiment that I conducted. And again, the experiment got very messy, and I had to end up throwing the materials out in order to avoid a bigger mess. So that's all I have to show for you today. Thank you for listening, and have a great day.